administration stuff. If somebody would ping the chat room to make sure that that's working, that'd be great. If somebody wanted to chime in and see if the voice is working. It was working yesterday, so I think we might have a good plan today. Okay. Okay, so today we are on week 6. Okay, so we're on week 9. So we're October 21st, 2020. We're going to be working on module 7 today. On Friday, we're going to start with a small lecture on module 7.3, which is SN1, SN2, E1, E2. And then during that, right after that, we're going to also have an activity. And so I'll mail out that activity on Friday. And basically just go ahead and work through it in your groups. And then I'll give you the instructions then, and then kind of upload it by midnight that night. And if you end up not coming to class for some reason, go ahead, just finish it yourself and upload it and get as many points as possible for your activity. And then on Monday, the 26th, we're going to finish up with the lecture for module 7.4, which is the actual reactions of alkenes and alkynes. And we'll have our review and our our next exam on October 30th. Okay, so for due this week, we had just module 7 on Top Hat. The homework, actually, I've moved to Wednesday, October 28th, because I realize I'm going to be lecturing the second half of that module 7, the last part of that module 7 on Monday. So I've moved the homework to Wednesday. And then that'll be also a great review. All of the homework will be released at Wednesday midnight, and so that you can start reviewing and studying for the exam. All right. So is there any questions about administration or what we're going to be doing this week? Go ahead and take a preemptive strike on a drink of water to make sure that's working. Okay, so without further ado, I will go ahead and bring up our last slide from module 7.1. Okay, so I'm going to go ahead and move this over here and get that over there. All right, so you should be seeing my slides now right here. And this is the last slide in our module, and it's talking about the stereochemistry of E1 reactions. Remember, the premise of an E1 reaction is that you have something that's going to leave first, giving you a carbocation. Whenever you have a carbocation, you have the opportunity for the carbocation to rearrange. If it can rearrange to a more stable carbocation, it will. If it can't, then it's just going to go ahead and produce its elimination products. Now remember, when we do our beta elimination products, that means we're removing a hydrogen from one carbon over from where our leaving group was. We want to form, if possible, the more thermodynamically stable product. Okay, so at the beginning of the chapter, we learned that disubstitution is more stable than monosubstituted. We also learned that trisubstituted is more stable than disubstituted. But within the set of the disubstitution products, the trans configuration is more stable than the cis configuration, so that when we look at our stereochemistry of a possibility of forming a cis or trans alkene, the predominant product is going to be our trans alkene because it is thermodynamically more stable than our cis alkene. Okay, so we'll see that time and again in our E1 reactions. These are slightly different in our E2 reactions, and I'll explain why in just a few minutes. Okay. Now, the other thing we have here is that even if you have more hydrogens from a different beta position here, again, you're going to form the more thermodynamically stable product, if at all possible, because you had your leaving group leave first. So you don't worry about sterics. All you worry about is thermodynamic stability. So in your E1 reactions, you're going to try to always form your more thermodynamically stable product. However, in E2 reactions, we have a couple constraints because it's bimolecular, and that's what we're going to talk about next. Any questions on the E1 and E1 stereochemistry? Yeah, if somebody could ping the chat, I don't have a chat coming up yet. So let me go ahead and pull up our chapter. No, we want to, there it is. Okay, so now we're gonna, okay, great, no questions. All right, so now we're gonna start E2 reaction. And the name implies it's an elimination reaction that requires two molecules to be together at the same time. What this means is that you cannot form a carbocation, either because it's a primary alkyl halide or a secondary alkyl halide, or it's a very bad leaving group. And so that you want to have some base come in and start tugging on a beta hydrogen before you start to break that bond. And so we're going to have some configuration limitations in how we can do this. But the idea is you have to have the base and the substrate in the same place at the same time. The base has to be pulling on a hydrogen. So we might run into some sterics issues here. And at the same time, those electrons from that hydrogen come in and kick out our leaving group. Okay, so that's the basic premise here. And let's talk through these each and separately. So we have, of course, in these reactions, a competition between the nucleophile and the base, okay? They're not exactly the same thing, but a nucleophile can be a strong or weak base, and a strong base can be a strong or weak nucleophile, but they're not exactly the same, okay? Now, because we have these strong bases that can act as nucleophiles, we have a competition. We have a competition between an E2 reaction and an SN2 reaction. Okay, so we have to look at the deep dark secrets about our E2 reaction to see which is going to be favored. Okay, so let's first talk about some of these basic examples here. So in this first case here, we have a primary alkyl halide, which means it cannot undergo an E1 because we're making a primary carbocation. So that's off the table right there. So our two choices here, because it's a primary, we can't go through a carbocation, so we can't go through an SN1, we can't go through an E1. Okay, so great. So now we have this competition between our substitution reaction and our elimination reaction. Okay, so in the case of this particular compound, this particular example here, we have our sodium ethoxide. So we have our alcohol, which is a weak acid. We've deprotonated, and now it's a stronger base. But it's also nucleophilic because it has that negative charge, okay? So in the presence of methanol as a solvent, that's a protic solvent, we actually see in this case at room temperature, or just barely above room temperature, we see the primary product is our substitution product, but we do get some of our elimination product, okay? So that tells us that we definitely do have a competition here. Now, let's take that primary substrate and turn it into a secondary substrate. Okay, so now your secondary substrate can form a carbocation sometimes, but in this case, because we have a strong nucleophile right here, in this case, it's slightly bigger than methanol, it's ethanol. What we can do is we can actually, we've actually substituted with methanol here. So this should actually be methanol and methoxide again, because our substitution product here. So we have a small nucleophile, but a strong base. And we have a secondary substrate. And in this case, the elimination product becomes the major product, okay? We still have some substitution product, but our elimination product becomes our primary product, just going from primary to secondary, okay? So that's telling us something about the availability of these beta hydrogens and the ability for that leaving group to leave because it was stabilized to some extent. Okay, now let's look at our third possible one where we have a tertiary alkyl halide. Again, we're not going to go through our carbocation system. What we're going to do is we know that our nucleophile can't come in and do a substitution reaction because it's too bulky. So now our SN2 reaction goes away, and our only possible reaction is our E2 reaction. Okay, so in this case, we only have our elimination product here. from our strong base, but it is too big to act as a nucleophile, therefore it eliminates to give us our E2 product. Okay, so now look at this trend. Small nucleophile primary gives us predominantly substitution. Small nucleophile but strong base and a secondary gives us a mixture of two, but we're starting to favor elimination. Okay, and if we heat this reaction up, we're going to even drive it further to elimination. Tertiary alkyl halide cannot undergo substitution reactions. Therefore, you have 100% of it as an E2 elimination. Okay, so let's talk about each and every one of those things and why and the different steps associated with it. Okay, so as the name suggests, it's a bimolecular reaction, meaning the base and the substrate have to be there at the exact same time. Okay, which means the rate depends on having a certain amount of concentration of the base and a certain concentration of the substrate. So that means that both of those concentrations are important to our rate law, which means we now have a second order reaction, meaning that if you double one, the rate doubles. If you double the other one, the rate doubles. If you double both, the rate quadruples. Okay, so being that it's a bimolecular reaction, that means that it doesn't form intermediates and it happens all at one time, or a concerted reaction. So we have a single hump in our coordinate diagram. Okay, so let's look at the different parts of this. So the first part is you have your base and your reactants dissolved up in solution. Okay, and then you have to have enough activation energy to have your electron, your negative side of your material to kind of fight past the electron repulsion to get close to a beta hydrogen on your substrate. Okay, so that's this rise in energy to get to that, just a break through all of those electron clouds to get to that position there. Okay, once it gets to that position now it acts as a base and it uses its electrons here to reach out and grab your hydrogen. That means the hydrogen electrons are now going to be put into a carbon-carbon double bond. When it does that, that means it pushes the electrons with the leaving group out. Okay, so if we look at where these electrons end up, the electrons that were out on this hydrogen bond right here have been used to make our double bond. The electrons that were in the sigma bond have been used to make the negative charge on our leaving group. Okay, and now our base is now turned back into its conjugate acid. It has been fully protonated, and now we end up with the only charged species being our leaving group. Okay, so if we look at our coordinate diagram here, we just have our activation energy is just that, kind of getting past the electrons. Once it's there, now we have our classical acid-base reaction, and our acid-base reaction will cascade down our thing to form our final products here. Now, in this case here, we're showing that we only have one choice for beta hydrogens. We either have beta hydrogens on a methyl group or beta hydrogens on a methyl group. So we only can form one product from this particular substrate. Okay. So that's the basics of an E2 reaction. We have to have our base and our substrate together at the same time. Our base has to pull on a beta hydrogen to get those electrons to make our new double bond. And then once our new double bond is forming, we break our sigma bond with our leaving group. Okay, so there happens to be a rule that suggests which beta hydrogen it's going to remove, okay? And like we talked about last time, our Zaitsev's rule is going to control which of the beta hydrogens leaves, okay? And it turns out that it's not just the number of hydrogens available to it, it's whichever gives us the most thermodynamically stable product, okay? And we can almost think of it like that hydrogen that has this on a carbon with more carbons on it is slightly more acidic, and therefore it can leave earlier than a hydrogen that's on a carbon with just a whole bunch of other hydrogens, okay? But the net result is you will get to the more thermodynamically stable product. And as we learned before, that our terminal alkene, let me blow this up. Our terminal alkene is our least stable of the alkenes. Then we come up with our cis and trans alkenes, trans being slightly more stable than the cis, and this exoethylene right here being slightly more stable than the trans. And then, of course, our tri-substituted and tetra-substituted are even more stable. Okay. So that means that when we have a choice between different types of beta hydrogens, we're going to choose the beta hydrogen that is on the more substituted carbon. That will always give us our thermodynamic product. Okay. And notice just in this reaction here, if we do this reaction at a reasonable temperature here, we still get a little bit of the other product, the less stable thermodynamic product. And that just happens in a small amount because it, statistically there are more hydrogens there that it can pull off. And if it starts to pull off on that one and gets enough over that transition state, it does produce product. But it's getting to that transition state, getting that more stable transition state to give us our more substituted alkene. Okay, so what does this mean with stereochemistry and regiochemistry? Okay, so ideally, you want to take a hydrogen off the more substituted carbon, and when you do so, you will almost always get the more substituted alkene. Okay, and part of that has to do with the idea that the methyl group that is adjacent to our hydrogen here can hyperconjugate with the hydrogens that are starting to be pulled off right here and help stabilize that intermediate. Okay, and when we stabilize that intermediate, we end up getting to the more thermodynamic product here as our regio-specific product. Okay, now, when a reaction specifically gets one isomer versus another isomer, we call that regioselective. And in this case, our elimination product is regioselective because it's going to form the more stable, the more substituted double bond. Remember, our double bonds here, because it's fixed in space and does not have free rotation, that turns it into a stereoisomer. Okay, so let's look at the two different transition states to help us kind of figure out why the more thermodynamically stable product is going to be created. Okay, so I'm going to blow that up a little bit. So in our first transition state where we're going to form the more thermodynamically stable part, it's actually easier for the base to come in and pull off the hydrogen on the more substituted product because those hydrogens are slightly more acidic. And because they're slightly more acidic, it's a slightly lower activation energy. And if it's the lower activation energy, it's going to become the major product, okay? Because more of the molecules have this energy than have this energy. Therefore, it's going to be this more, the more stable product. Now, statistically, because there are more of these hydrogens here, that there will be enough energy to have some of those higher energy transition states to occur because of the number of hydrogens you have. But you don't have as much of these molecules with that much heat. Therefore, it is not going to become the major product because we don't have as many molecules that have enough energy to get into that transition state. But once you do get in that transition state, you're pulling off your beta hydrogen off that less substituted carbon, which leads to our less substituted alkene, which is our less thermodynamically stable product. Okay, so it all has to do about that transition state, and the lower energy transition state is always pulling the hydrogen off the more substituted carbon. Okay. Oops. All right, so let's think about that transition state in another way, okay? So if we look at the transition state in another way, because the base is coming in and pulling on that hydrogen, and the electrons from that hydrogen-carbon bond are coming in to form our double bond, and then the electrons that were on our leaving group leave with the leaving group, That means we have to have a specific orientation in space to make this happen. Okay, so if you can think about going through this transition state, we start having these sp3 hydrogens here, coming here, go through a transition where they are no longer sp3 hydrogens, they're sp3 electrons, they're turning into pi electrons, p electrons. And those p electrons then become that new pi cloud. Okay, but there has to be a way to do this where we have those electrons come in and make that pi bond. So let's look at it from a Newman projection. Okay, so this is our Newman projection. If you'll remember, our Newman projection is where we are looking down a sp3 bond, a sigma bond, and we're looking at one of the carbons is out toward us and the other carbon is behind. Okay, so the one that's out toward us is the one with the solid lines here, right here. And then the one behind is, of course, the ring, and then the solid lines coming out from that those are the atoms that are in the back. Okay, so in this particular configuration, as our base is pulling off these hydrogens here, it needs to be anti, so basically completely opposite or trans from the leaving group, so that when the electrons come in, these electrons can go out. So we're all coming in at the same time. Okay, let's look at that again from the side, right here. So our base is coming in here to pull these off. These electrons are going to kick in, and then these electrons are going to kick out. The electrons that come in here are going to be the ones that form that new pi bond. So that means that hydrogen and that leaving group have to be completely opposite each other, what we call anti-configuration. And so whether you see it better as this side view or whether you see it better as the Newman projection, you have to figure out if you have multiple groups on your thing. Let's say we have a different R group here and an R group here, you can actually predict the stereochemistry of the product by making sure that your hydrogen and your leaving group are in this anti-configuration, and you will be able to predict the stereochemistry of the product. Okay. So because this is a necessary transition to go from that, because remember, we start with an sp3 tetrahedral carbon. We're taking an sp3 bond, sigma bond, taking those electrons, turning them into p orbitals. That means that these are now trigonal planar sp2s, so they have to flatten out. And as they flatten out, they have a top side where the electrons are coming in and the bottom side where the electrons are leaving. Okay, and so that's how another way to think about how these have to be opposite each other. So as they go from their tetrahedral structure, they go to their trigonal planar structure and form that new double bond. Okay, so that's pretty easy to see when you have a free rotation available to you. But what if it's not like that? Then we have to worry about see if we can find a configuration in, let's say, a ring where we can make that anti-configuration happen. Okay, so from an orbital perspective, we're just doing this transition from our sp3 to a p orbital. And if we think about it here, the shape of our sp3 is this large dumbbell with this little teeny part here, and the bond going to the leaving group also is an sp going here. But at the beginning, when it's bonded here, the larger lobe is on this side. Okay, but because these electrons are being removed from here, we change the lobe shape and they transition from that sp3 to an sp2, and then this is the free p orbital on each of those adjacent carbons. With those p orbitals now having a total of 2 electrons, we now have a pi bond. Okay. So, it's kind of like in the transition with an SN2. We actually, in the SN2, we actually have it coming to the backside of the sp orbital, generating a new formation and then breaking it. And we're actually changing the lobe from being on one side of the reaction to be on the other side of the reaction. That's how we get inversion in an SN2 mechanism. In this one, we get that inversion, but we also get a transition to the P's that can be adjacent to each other and coplanar with each other to form that pi bond. So if these have to be in that position, that means that in certain rotations, it's not going to happen. This reaction won't happen. So in our anti-configuration, where our hydrogen is in a Z configuration with our leaving group, this is the fastest reaction. It's where the hydrogen and the leaving group are 180 degrees apart, and it makes it easiest to form that pi bond. Okay. However, it is technically possible to do it where you remove it from this side where they're coplanar, they're at 0 degrees, but most of the time that is fairly, it's a higher energy configuration state. And because of its eclipsed conformation, it's a higher energy configuration state. So, well, theoretically it can happen. It probably doesn't happen most of the time. It's going to be this trans configuration, 180 degrees apart, that's going to happen. Okay. Now, let's say we had a different configuration like a gauche. And if we look here, we have the hydrogen that was 90 degrees off of the bromine. Okay. Now, when these are trying to transition to form those p orbitals, the p orbitals are going to be out of alignment with each other. And that's going to create a very high energy state. And therefore, when they are not in that 100%, 180 degree angle, when they're in the gauche position, the reaction does not happen. Okay, so our primary reactions when they're anti are rare occasion when they're have a 0 dihedral angle, but anytime they're in any gauche condition, they do not react. Okay, now this is important because now that you know where they have to be, you can now know where your other groups are, and that controls your stereochemistry. Now, one of the easiest ways to watch this, because in a regular alkane, you have free rotation around that sigma bond, the easiest way to look for it is when in a cyclohexane. And we do it in a cyclohexane because we have 2 possible configurations for our leaving group if everything else is hydrogen. It can either be axial, where it's in that higher energy state, or it can be equatorial in that lower energy state. But in one state, we can have elimination. In the other state, we can't because they'll be in the gauche. So let's look at that in detail. Okay, come on. All right, so let's look at the one where we need to have them in that 180 degrees apart, right? So the only way to get our bromine and a hydrogen 180 degrees apart is to have them both be axial, okay? Because when they're in the equatorial positions, if they're both in equatorial positions, that puts them 60 degrees off. So that puts them in a gauche position. So we have to actually wait for the ring to flip back and forth until the bromine and the hydrogen are both in axial positions. Once they're both in axial positions, we can have our base come in and interact with our hydrogen here. Then our hydrogen is anti to our leaving group, and our electrons can kick in, forming our double bond. And then our electrons can kick out with our leaving group, giving us our alkene. Okay, so the net reaction happens because both the hydrogen and the leaving group are in the axial position. Okay, so let's look at if we had it in the equatorial position. If we have it in the equatorial position and we look at this hydrogen here, this hydrogen is Gauss to the leaving group, and that reaction doesn't happen. This hydrogen is Gauss to the leaving group, meaning it doesn't happen. So let's look at that just down this purple bond right here, or sorry, down this red bond right here. If we're looking down here, this hydrogen is Gauss to our leaving group, and then this hydrogen is also Gauss to our leaving group here. Let me erase. Erase. Okay. Again, looking down this red bond here, and so we have this bromine in front, right here, and this is one of the hydrogens we can pull off. This is the other hydrogen can pull off. Both of these hydrogens are now 60 degrees off of the leaving group. Therefore, neither of those hydrogens can be removed to create a double bond. And then if we flipped it the other way, we would see, if we go down the purple bond, we see the same thing. We see our hydrogens are both 60 degrees off, which means in this configuration, this does not do your E2 reaction. We have to wait. We have to add heat till it flips into the where we have a hydrogen and the leaving group both in their axial position. Okay. So now that we have both of those in our axial position, that's going to tell us something about our product distribution as well. Okay. So for example, let's say we put one of these really big, huge groups on our cyclohexane. So this is a big T-butyl group, and so it will be at the equatorial position 99.9% of the time because it's just so big. Okay, so that's going to dominate where that bromine is and which hydrogen is available to it. Okay, so in theory, if we were to look at this, we have two hydrogens here. We have one hydrogen in a methyl group. We would want to put the double bond here because it would give the more substituted double bond. It'd be a tri-substituted double bond. However, because we cannot get a hydrogen in, and we have to have an axial hydrogen to be able to remove that bromine, we actually don't form that product. And let's show why, okay? So if we look at this using, again, that side view, okay, because this group right here is so big, it's going to have to be in the equatorial position, okay? So if that forces that in the equatorial position, we have this methyl group is going to be up, this hydrogen is going to be up. So we have this methyl group in an axial position, this hydrogen in an axial position, this bromine in an axial position, okay? Which means we cannot remove this hydrogen. That hydrogen is in the equatorial position, meaning it's gauche to the leaving group. Okay. So that means the only hydrogen available for us to actually deprotonate is the one that's axial, which is on the least substituted side, giving us our less substituted product, but it is the only product available to us because we had to remove the hydrogen that was anti to the leaving group. So sometimes, and this is a good example of that, you can get the least substituted product because of available hydrogen and the availability to form that anti-configuration in our E2 reaction. Okay, so let's try to predict the stereochemistry using this one right here. And again, we're going to use this T-butyl group here as a big group. And we know that it's always going to be in our equatorial position. And now that we have our bromine and our methyl group at the same position, we have to kind of look and see where they are. So in one configuration here, in this configuration, we have our T-butyl group in our equatorial position. Okay, that's not going to happen very often. Okay, and not only that, it also puts our bromine, our leaving group, in an equatorial position. Okay, which means this particular configuration, number one, it doesn't happen very often, but it won't react. So we have to wait for it to go to have the bromine in an axial position. And in this case, it actually is the more stable conformer because we have this in an equatorial position because it's the big group and it wants to be on the axis. I mean, on the equator of the molecule here. Now that we have that, we can see that we have actually two possible axial hydrogens. Okay, so in this particular configuration, we can get elimination of this axial hydrogen. And when we eliminate, let me recolorize these. We have two hydrogens possible. We have this blue hydrogen here, which is axial to the bromine, which is also axial. And then we have the red one. In the case of this blue hydrogen here, because it's in this anti-configuration here, when we eliminate that, we'll actually end up with this product here, okay? Giving us the double bond between because we're moving the hydrogen next to that methyl group, giving us our tri-substituted alkene. Okay. However, because we have this axial hydrogen that is also anti to the leaving group, we can also form this product from the removal of this hydrogen here. Okay. So based on what we know about stability here, okay, we can form both products, but which one is going to be the major product? Go ahead and type in the chat room. Or shout out. Okay, which one of these is going to be our major isomer? Right. So because we have two possible axial hydrogens that can form the disubstituted alkene and the trisubstituted alkene, they both can form, but our trisubstituted alkene is the more thermodynamically stable, and therefore it will be the major product. Now both products form, but it's going to be our major product. Okay. All right, so let's talk about the Zaitsev's rule as far as stereochemistry goes. Okay, in a long chain alkane, you're always going to try to form the more substituted isomer if at all possible, and because you're not limited by that configuration. In the constraints of a ring or some other sterically controlled system, you might have to choose the seemingly less thermodynamic product. But in general, for all straight chain alkanes, you're in competition. And so you have 3 hydrogens possible here, 2 hydrogens possible here. So you do get a little bit of that less likely product, which is our lowest stability. So we're going to have, this is our lowest stability because it's a monosubstrate alkene. Our cis is going to be less stable than our trans, and so it will be there, and it will be found there. And then our primary product is going to be our trans alkene because it's the most thermodynamically stable. Notice it's not 100% of just the trans alkene because we have the possibility of going through those 2 different transition states. Okay, but in general, we always go to the more substituted and more trans-like alkene. Okay, so why does the trans dominate over the cis-butene? In addition to, because they're really close thermodynamically and they have the same transition state. So the idea is, where are the different groups are? And so you want to think about it as the trans is going to give us where the 2 large groups, assuming that you can have a hydrogen and the bromine 180 degrees apart, you also want the 2 largest groups 180 degrees apart as well. So let's look at that. So in this case right here, we have the hydrogen and the bromine 180 degrees apart. So let's draw our Newman projection of this right here. So we have our hydrogen here, we have our bromine here in our anti-position here. And this one right here, we have our bromine here. So we have a methyl group here, CH3, and a hydrogen here. So that's this hydrogen and this methyl group. So now let's go with, let me go ahead and draw this as the red hydrogen so we can see it right here. And then we have right next to that, behind it is the methyl group, CH3 group. And then we have our blue hydrogen here. Okay, so the first thing we want to note is that, oh, look, our hydrogen and bromine are 180 degrees apart. So that's great. So these are in a great configuration for it to actually go through the E2 reaction. But the other thing to note here is that our 2 largest groups now are also 180 degrees apart. That is going to be the more stable configuration. That more stable configuration is going to give rise to our trans product. Okay. So if we do the same Newman projection here, we're going to start with the bromine side. Here, we're going to look at this right here with our bromine down. Our methyl group is going to be here again, and our hydrogen is going to be there again. And let's go to our blue hydrogen, which is the one is going to be up. Our red hydrogen is going to be over here. And now our methyl group is going to be over here. Okay. So in this configuration, our two methyl groups are gauche. They're 60 degrees apart here. And even though we have a hydrogen that's at 180 degrees off of the bromine, we have a less stable configuration because the two largest groups are gauche to each other. Okay, so this is a great argument about why we see the trans as the dominant product over the cis. In both of the transition states, we have 180 degrees between the hydrogen and leaving group, but we have the additional element of stability of the next largest groups, or the largest groups. Questions on that? All right, got a couple more slides here and then we can and so this is this is that same argument kind of drawn out in nicer kind of configuration here. So the idea here is that when you review these notes, you want to look at having your large non-active substituents be 180 degrees apart, if at all possible, after you first make your hydrogen and your leaving group 180 degrees apart. Okay, so that is going to give you the more active, it's going to give you the fastest reaction because of there's more of it in this configuration because it's the more stable configuration, and it'll react faster to give us our more stable product, which is our trans. Here, this is going to be in this configuration less of the time. It also gives us a less stable transition state and our less stable product. Okay, so let's look at that as an energy barrier thing. So the energy barrier difference comes from the fact that we had to add energy to the system to rotate it around to get those in that gauche system. Remember when we just talked about, having the methyl groups there at the farthest apart, that is our lowest energy state. And then when we eclipse, it goes up. And then when we get to gauche, it goes down again. And when we fully eclipse, they go up again. And then when we gauche, they come down. And then until we finally get to that 180 degrees with our two largest groups is always our lowest energy configuration. So if we're starting out with a lower energy, it takes less energy to get to that transition state to give us our product. And it just happens to also form our more thermodynamically stable product. Okay. So another way to look at this where we don't have to redraw everything is if we have chiral centers, we want to try to figure out a way to draw it so that our hydrogens and our bromine are in their most stable state first, okay? So in this case here, we're looking at a way to draw a diastereomer right here. It's got two stereocenters here. And so we want to find a way to get either this hydrogen, and in this case, we've marked it with deuterium so we can see which one's leaving, okay? So we're going to have either this hydrogen or this deuterium leave because our leaving group is on the other carbon. Okay, so if we want to look at that right here, the methyl group and this carbon and this methyl group here are going to be the two groups that control the most stable intermediate transition state, okay? They're going to control where it is. So if we draw this here, remember that when we have this type of projection here, the ones that are in the straight lines are going down, the ones that are sticking out to the sides are coming up. So when we redraw that as our stick figure here, it's going to look something like this, okay? Now that's just how to draw it from here to here, because notice the methyl group down, hydrogen, bromine up, hydrogen and deuterium up. Now we want to rotate that around till our methyl groups are opposite each other so that they are 180 degrees apart. And when we do that, we have our methyl group here and our methyl group here. And now in this case, we have our bromine 180 degrees away from our deuterium. So if our bromine is 180 degrees from our deuterium, that's the one that's going to be removed to give us our trans isomer. But let's say we rotate it a little bit further and actually put our methyl groups in their Gauss configuration so that we had the hydrogen 180 degrees from our bromine, we would end up with the cis isomer. Okay, so you can do that again on the next example here, but again, it's the transition from our projection here to give us, remember these are always down, to give us our redrawnness, and then try to draw it so that our methyl groups are 180 degrees apart, and that determines which of the hydrogens you will remove to give your primary or major product. Okay, let's see what we got. All right. I think I got, all right. So that leads us to something else. Okay, so in all the cases above, we were looking at small bases, ethoxide, methoxide, primary alcohols that have been deprotonated. Okay, now, is there an effect based on the size of the base? Yes, there's a huge effect with the size of the base, okay? And it has everything to do with the idea that you cannot get a large base to get to that secondary beta hydrogens. When the base gets too big, you can only get to the primary beta hydrogens. And so the primary beta hydrogens would be the ones on these methyl groups. The secondary beta hydrogen is going to be the one on the CH2s right here. So when we have small bases like ethoxide and methoxide, the predominant product is the more substituted product, the Zaitsev product, okay? But once we start using a large base, like in this case, we're using T-butyl, okay? This is the classical large bulky base. If you learn, if you have to latch onto a large bulky base, this is your first large bulky base to think about. It is now too big to come and get these beta hydrogens on that secondary carbon, and therefore our product ratio starts to shift to the less stable product. It's what we call the Hoffman product, okay? Hoffman is basically telling us that our base has gotten so big that we cannot get the thermodynamic product, we're going to get the kinetic product from this. And so we end up moving away from our more stable product to get to our less stable product because of availability of that big base to come in and do it. And then if we get even bigger, right here, we actually can decrease that product ratio of the more stable product to even greater. Okay, now, are these our only big bulky bases? No, we have a couple more we're going to talk about, but the idea here is when we have our ethoxide, methoxide, especially in ethanol and methanol, we're going to look for our Zaitsev product. When we start moving to big bulky bases like T-butoxide and a couple others we'll talk about later, we start looking at the less stable product, or what we call the Hoffman product. So it's the kinetic product based on that bulky base. I think, okay, yeah, let me just go ahead and do the Hoffman rule. Okay, so instead of moving that secondary hydrogen, we can't get our big bulky base. If you think of our big bulky base as, basically being a beach ball with a negative charge on one end of it, right here, it can't come in and get to this site here. So instead, our beach ball with our negative spot on it right here comes into the other side and gets those less sterically demanding hydrogens. And when we get that, we end up with our Hoffman product, or our less substituted product. Okay. All right. So we're right at 10:50. If you have to go off to class, go ahead. I'm going to stop recording. If you want to hang around and ask a couple questions, please do. Okay, give it a minute for it to stop.